Hello, welcome to our presentation on methanol production from synergistically integrated natural gas reforming and biomass gasification. The work has been done at MIT Energy Initiative with my colleagues Dr. Bromberg, Dr. Cohn, and Dr. Genser. To give you motivations for this work, low carbon liquid fuels are needed for transportation and other difficult to electrify sectors, especially when grid electricity does not have a high share of renewable power. Biomass conversion to liquid fuel is one of the main pathways to produce low carbon fuels, but the carbon conversion efficiency of the conventional BTL process or biomass to liquid process is low. Carbon conversion efficiency is important because there is limited amount of biomass. In this work, we have examined two process configurations for significantly improving this efficiency. When we look at the conventional biomass to liquid process or BTL process, we see that biomass is gasified in a gasifier, where here we have chosen an entrained flow gasifier where oxygen is needed, and that is provided by an air separation unit. Syngas is a mixture of hydrogen and CO, but the hydrogen content in the syngas is low, and what is conventionally done is to increase that in a water gas shift reactor, where part of CO is converted to CO2 and hydrogen. But the downside is that we need to separate the CO2, and that is the reason for low carbon efficiency in this process. More than 50% of carbon is lost as CO2. So to continue with the motivations, we want to provide optimal utilization of both carbon and hydrogen in biomass. Conventional BTL processes have low carbon efficiency because the syngas is deficient in hydrogen. Natural gas, on the other hand, is rich in hydrogen. And through synergistically integration of syngas generated from biomass and natural gas, we can produce the right composition for methanol synthesis without much loss of carbon as CO2. Methanol production is the liquid of focus here. It is an important chemical feedstock and a high octane fuel. And compared to Fischer-Tropsch process, which is used for producing jet fuel, diesel, etc., a methanol process is simpler in production and purification. Here we have not considered the co-feeding of natural gas and biomass in the gasifier for several reasons. One of them is that the hydrogen to CO ratio of the produced syngas would not be high enough for methanol synthesis. That is because the hydrogen would react preferentially faster with oxygen than other fuels in the gasifier. Moreover, the gas cleaning would be more difficult because of increased flow rates. And another reason is that methanol production would be coupled to both natural gas and biomass. So the approach we used is the parallel reforming and gasification, where we have increased the feed flexibility because gasifier and reforming process are fully decoupled, and natural gas is used as swing fuel. Therefore, we can have the right hydrogen to CO ratio for methanol production without much loss of carbon. And our aim is to have more than 50% of carbon entering the plant to be from biomass, but we can have 100% carbon from natural gas as well. So some of the results from the conventional BTL that I showed before, and this is the base case for our comparison. As you can see, the more than 50% of carbon is leaves as CO2, and the carbon efficiency would be 44%. I've also shown the energy flow in thermal units, and for that we have assumed the thermal power to electrical power of 50% efficiency to convert electrical power to thermal power, and that would result in 58% energy efficiency. We have considered the 134.1 thermal input from natural gas and biomass to be constant in this analysis, and also in the next designs that I'm going to show you. So the first proposed design is utilizing autothermal reformer, or ATR, and solid-oxide electrolysis cell to provide the hydrogen and oxygen. As you can see, these units are the natural gas reforming and gasifier are in parallel and decoupled. The SOEC is producing the hydrogen and oxygen needed for the plant. So we produce just enough hydrogen and oxygen for this process. Therefore, it does not need a separate air separation unit. We do not also have a separate acid gas CO2 removal unit. And the acid gas removal here is mainly to remove hydrogen sulfide from the biomass. Therefore, we have high carbon conversion efficiency, and here are the results for this case. As I mentioned, we aim to have more than 50% of carbon from biomass, as it is shown here. This would give us about 90% carbon conversion efficiency, and on the energy flow, thermal energy flow, we can see more about 55% thermal energy to methanol. And as I mentioned, we have kept the total thermal input from natural gas and biomass at 134.1. And this is the ratio we would get to have more than 50% of carbon from biomass. We have also looked at the availability of heat within the process by drawing the composite curves, and we can see we have enough heat in the process, and we do not need any external heating. This is in the case of proper heat integration within the process. We also have excess heat of 42 megawatt, mainly low temperature heat. The second design that we proposed here is using ATR, autothermal reformer, and gas heated reformer, or GHR. So what is ATR gas heated reformer? Gas heated reformer is similar to a steam methane reformer, where catalysts are in tubes, are packed within tubes, and the heat is provided on the shell side. So this is similar to a steam methane reformer, but the difference is that we are not using a furnace to provide heat. We are using the ATR outlet exhaust stream, which is at high temperature here, 1050 degrees C, to provide the heat for steam methane reforming. Therefore, we have the advantages of steam methane reforming, but we are not producing CO2. Here, we also have air separation unit to provide oxygen. The syngas generated from natural gas is rich in hydrogen, but it's not high enough when combined with biomass syngas to have the right composition. Therefore, we need to separate part of its CO2. We can increase the hydrogen content by water gas shift reactor. So part of CO is shifted towards CO2 and hydrogen. And one of the synergies that we can utilize between reforming and gasification is so that they have the same as CO2 removal unit. So we are not going to build a new CO2 separation unit. They can share the same unit and separate part of the CO2. Here are the results for this case. We can see the carbon conversion efficiency is 70% in this case. And again, the total thermal input from natural gas and biomass are kept constant at 134.1 megawatt thermal. And the energy efficiency is 68%. We have also looked at the composite curves to see if we have enough heat within the process. Again, this process is also has enough heat, and we do not need any external heating. We also have low temperature heat, excess heat available, which is 34 megawatt, which can be utilized. This is the summary of the cases I've shown where we have the BTL, conventional BTL on the right side, and the two new designs shown here. The carbon conversion efficiency is increased by 1.6 times in case 2 and 2 times in case 1 compared to the BTL process. The process CO2 emissions are decreased by 3 times and 13 times compared to a conventional BTL process. So both designs have lower process emissions than the conventional BTL process. Case 1 has the highest carbon conversion efficiency, but it is more expensive than case 2, as you can see here. But we also have a higher methanol production. So the specific cost increase is only 8%. Case 1 is heavily dependent on renewable power, which is 45 megawatt to be used in electrolysis. And the BTL is the least favorite because it's most expensive with highest process emissions. We have also done levelized cost analysis of the process, where we have the two new designs on the right side and the conventional BTL on the left side. And we can see both proposed designs have lower levelized costs than a conventional BTL process. Here we have utilized average electricity price of $100 per megawatt hour. But that's an important variable, so we have looked at it more closely, and we have changed the electricity price from $0 to $150 per megawatt hour. And we can see case 1 is heavily dependent on the electricity price. By considering electricity price of $100 per megawatt hour, the case 1 is 5% cheaper than the conventional BTL, and case 2 is 30% cheaper. A quick point about the feed flexibility. The proposed processes can operate flexibly on either one of biomass or natural gas and any combinations in between. and also natural gas acts as a swing fuel. A few key takeaways. Here we have proposed designs that can significantly improve carbon efficiency of methanol production by combining biomass gasification and natural gas reforming. These processes are fully decoupled and flexible, and natural gas is used as swing fuel. Through parallel integration of natural gas reforming and biomass gasification, we can increase the economic and environmental appeal of fuel production from biomass, mainly by reducing the methanol production cost by 5 to 30% and reducing process CO2 emissions by 65 to 90% compared to a conventional BTL process. And with that, I want to thank you for your attention, and please let me know if you have any questions or feedback. Thank you very much for your attention.